Hi everybody, let us see the effects of quantization by truncation and rounding in number representation in DSP systems. In fixed point or floating point arithmetic operations, the size of the result of an operation may be exceeding the size of binary used. So in such cases, the lower order bits have to be eliminated in order to store the result into the specified memory location. So the two methods of eliminating these lower order bits are truncation and rounding. The process is known as quantization by truncation and rounding. Have to be eliminated. I'll write it here. Have to be eliminated. So the process of rounding or truncation is called quantization. So the effect of rounding and truncation is to introduce error whose values depend on the number of bits eliminated. Let us see the characteristics of errors introduced through truncation and rounding depending on the number system. So let us start with decimal number system that are encountered as filter coefficients, sum of some values, products of two values, etc. Even in convolution or in correlation. Numbers, decimal numbers that are encountered in DSP applications will usually rise in the range of -1 to +1. -1 volt to +1 volt. Right. When B bits are used to represent decimal numbers, then 2 power B binary code words are possible. Okay. So the range of decimal numbers has to be divided into 2 power B steps. Okay. Each step is represented by a binary code. So each step of decimal number is called quantization step. It is called in the name of quantization step. Let me say what is quantization step. Q is equal to range divided by 2 power B, which is equal to 1 minus of -1, because the range is 1 volt, -1 volt to +1 volt. Maximum minus minimum, 1 minus of -1 divided by 2 power B, right? So which is equal to 2 divided by 2 power B, which can be written as 1 divided by 2 power B minus 1. I can even mention this as small b, 1 divided by 2 power B, which can be written as 2 power minus B, quantization step. So let me proceed. If B, small b is equal to B minus 1, then it is called the size of binary which excludes the sign bit. Okay. Therefore, the quantization steps of decimal numbers that lie in the range of -1 to +1 can be divided into -1 to +1 will be divided into -3 into 2 power minus B, -2 into 2 power minus B, -1 into 2 power minus B, 0 into 2 power minus B, 1 into 2 power minus B, 2 into 2 power minus B, etc. up to 1. Okay. So the quantization steps that lie the range of -1 to +1 can be viewed for small b is equal to 2 and small b is equal to 3 using the tables. I'll show you. Binary code word 000 will be used to represent 0 multiplied by 2 power minus 2, because we have taken b is equal to small b is equal to 2. So 2 power minus b, which is equal to 0 into 1 by 4, which is equal to +0 in sign magnitude. In 1's complement, it represents 0 into 2 power minus 2, which is equal to 0 multiplied by 1 by 4, which is 0 only. But in 2's complement, the same 000 will be represented to represent 0 plus 0 only. Okay. If you look at the second code word 001, you will come to know 1 multiplied by 2 power minus 2, which is equal to +1 multiplied by 1 by 4, which is 0.25 plus 0.25. The same in the case of 1's complement as well as the same in the case of 2's complement also. If the code word is 010, it is used to represent 0.50 as per the explanation given here. 2 into 2 power minus 2, which is equal to +2 into 1 by 4, which is equal to 0.5. So the same value will be, the same code word will be used to represent the same value in sign magnitude, 1's complement as well as in 2's complement. Similarly, 011 will be used to represent +3 multiplied by 2 power minus 2, which is +3 multiplied by 1 by 4, which is 0.75. It is the same number in all the three formats of number representations. Okay. But if you look at the next code word 100, it is so special. In sign magnitude, it is used to represent minus 0 multiplied by 2 power minus 2, which is minus 0 multiplied by 1 by 4, which is minus 0. Whereas in 1's complement, it is used to represent minus 3 multiplied by 2 power minus 2, which is equal to minus 0.75. But if you look at minus 4, it is in 2's complement, it is minus 4 multiplied by 2 power minus 2, which is minus 1. So like this, you will come to know only for negative numbers in sign magnitude, one set of numbers will be represented by the code words, whereas in the 2's complement, another set of numbers will be used to represent. You can see the variations. Plus 3, next to plus 3 you are getting minus 3 in 1's complement. Then for in sign magnitude you will get plus 3, after which you will get minus 0, minus 1, minus 2, minus 3. Whereas in 2's complement plus 3, afterwards you will go for minus 4, minus 3, minus 2, minus 1. So you can see the variations. This is the quantization steps used for capital B is equal to 3 and small b is equal to 2 in sign magnitude 1's complement as well as in 2's complement. Okay. Whereas if you take the same quantization steps for capital B is equal to 4 and small b is equal to 3, you will come to know about it. All zeros will be used to represent plus 0 in the case of sign magnitude as well as in 1's complement as well as in 2's complement. Whereas you can see variations only when you go for 1 triple 0. There you will come to know after plus 7 you will have minus 0 in the scale. Minus 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7 in sign magnitude. Whereas in 1's complement it is plus 7, after which you will get minus 7, minus 6, minus 5, minus 4. It will be decreased. Whereas in the case of 2's complement plus 4, after which you will get minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, etc. So this is the regular arrangement steps followed as far as the code word used for each step. In the case of sign magnitude, in the case of 1's complement, in the case of 2's complement, in fact, right? So let me illustrate it with the help of a diagram also. You will find out the truncation is the process of reducing the size of the binary number, actually binary number, because discarding, you are discarding something by discarding all the bits less significant, which are considered to be lesser significant than that of least significant bit that is retained. Okay, truncation is the process of, you may have to define it in the examination. What is definition is very important. What is called as truncation? Truncation is the process of reducing the size of binary number, reducing the number of bits in the binary number by discarding all the bits less significant than that of least significant bit that is retained. In the case of truncation, the binary number, say for example when it is truncated to b bits, small b bits, all the least significant or less significant bits beyond bth bit will be discarded. So that is illustrated in this case with the help of a staircase approximation truncation characteristics. This is called truncation characteristics. In the examination, you may be asked to draw the truncation characteristics of 2's complement quantizer as well as 1's complement quantizer. Kindly make a note of it. In the examination, there may be a question about illustrating the figure, or you may be expected to draw the picture of truncation characteristics of sign magnitude or 1's complement quantizer. You will find out that if you have told 0, 1, 2, 3 is the scale, whereas after which you will get in the case of 2's complement, you can immediately see that the next code word will be, do you remember the series with which the numbers were delivered? 0, 1, 2, 3 is on one side. You can see that 0, this is 1, this is 2, this is 3. Yes, with the small b is equal to 2, you can go up to plus 3, whereas the reverse order you have to start from minus 4, minus 3, minus 2, minus 1. Can you find out? This is what I say. This is about minus 4, minus 3, minus 2, minus 1, etc. Minus 1. So how many values are used? In this side you will have 4 values, on the other side you will have 4 values. So obviously we will go for how many values? 8 code words exactly. So for this interval you will have a code word, for the next interval you will have another code word. Okay. In the case of 1's complement, you will find out from 0 to plus 3, everything is as usual. 0 to plus 3 is as usual, but in this case from minus 3, minus 2, minus 1, 0 you will have. So this 0 will be indicated by 2 numbers, plus 0 on one side when you count in this direction, whereas when you count in this direction you will have minus 0. That is the key behind 1's complement representation. 0 will be represented with the sign plus 0, minus 0, whereas in the case of 2's complement there is no such variations. Okay, you will have only 0, only once, that's all. 0, 1, 2, 3 on one side, whereas on the other side you can see that the values will be minus 4, minus 3, minus 2, minus 1. So these are all the truncation characteristics. And interestingly, when you start discussing about the characteristics of the quantizer using the above picture, you will be finding out some interesting facts. Any positive number in the unquantized range between 0 to say for example 1 into 2 power minus b will be assigned with the quantization step of 0 to b only. 0 to 1 into 2 power minus b will be represented by 0 to b 0 into 2 power minus b only. Any positive unquantized number in the range of 1 into 2 power minus b to 2 into 2 power minus b will be assigned with quantization step size of 1 into 2 power minus b only, and so on. It will go ahead. But if you start believing at the sign magnitude in 1's complement quantizer, any negative unquantized number between minus 1 to 0 will be assigned with only one quantization step, that is 0 into 2 power minus b. Any in signed magnitude as well as in 1's complement quantizer, any negative number, unquantized number in the range of minus 2 into 2 power minus b to minus 1 into 2 power minus b will be assigned to minus 1 into 2 power minus b only, and so on. So these are all the 4 interesting facts you are supposed to express as the inference of the graph which has been drawn earlier or shown above. Okay, whereas in the case of 2's complement quantizer, any negative number, unquantized number within the range of minus 1 into 2 power minus b to 0 will be assigned with the quantization step of minus 1 into 2 power minus b. Whereas in 2's complement quantizer, any negative unquantized number in the range of minus 2 into 2 power minus b to minus 1 into 2 power minus b will be assigned to quantization step of minus 2 into 2 power minus b only. You can see that in the diagram. Okay, you can notice it. Any number, I'm ready to even blow it up. See, I'll show you this. Any number within the range of 0 to 1 into 2 power minus b will be represented by assigned to 1 into 2 power minus b only. Any number that is between 1 into 2 power minus b to 2 into 2 power minus b will be assigned to 2 into 2 power minus b only, and so on. Whereas any number between 0 to 2 into 2 power minus b to 1 into 2 minus 1 into 2 power minus b will be assigned with only one step, that is minus 1 into 2 power minus b only. You are going to simply express all these the keywords or the picture, the nature of the picture, characteristics in the words, sentences. So if you do like that, you will be surprised to see when I take an unquantized fixed point number and fixed point binary number quantized by truncation as nt, you will find out the error will be simply nt minus n. Isn't it? It is called a truncated number, fixed point quantized number by truncation minus unquantized number. That will be usually called as truncation error. The nature of the error will be expressed in terms of some numbers. So 1 into 2 power minus b to 2 into 2 power minus b is represented by 1 into 2 power minus b, for example. Then the minimum error will be 1 into 2 power minus b minus 2 into 2 power minus b, which is equal to minus 2 power minus b. Maximum error will be 1 into 2 power minus b to minus 1 into 2 power minus b. So you can see the difference. Unquantized number nt minus, can you identify? This is called nt. This is called nt, and this is the minimum error will be, this is n, unquantized number. Nt minus n will give me the error, whereas maximum number nt minus n will be giving you the value. So you can notice it. The difference will be, some cases it is in the range of 2 power minus b to, error will be in the range of 2 power minus 2 power minus b to 0 only. Whereas in the case of sign magnitude and 1's complement of a negative number representation, you will find out the error will be 0 and 2 power minus b. It is highlighted as 0 to 2 power minus b. Right? If you go for negative number representation using 2's complement, you will be surprised to see the range of a division quantization step. If a number lies between minus 1 to 2 power minus b, it will minus 2 to 2 power minus b, it will be simply equal to minus 2 into 2 power minus b. So the error will be minus 2 power minus b to 0 only. So the range of errors are all tabulated here. This range may be asked in the examination. Range of errors by truncation in fixed point number representations. So such a table has to be remembered by the student. So you must know the characteristics thoroughly. From the characteristics, you should know what will be the assigned step if a number falls between a particular range. In that range, what is the minimum number, what is the maximum number, you should know. And if it is truncated by only one number representation, so obviously nt minus n will give me the error. What is that error? Error should be, the range of errors should be remembered by the student. Is expected to remember. So for the truncation of negative numbers represented in sign magnitude as well as 1's complement format, the error is always positive because the truncation basically reduces the magnitude of the numbers. Whereas in the 2's complement representation, the effect of truncation on negative number is to increase the magnitude of the negative number, so the truncation error is always negative. This is like summary of the effect of truncation. in negative number representation, especially in sign magnitude as well as in 1's complement as well as 2's complement format. So 1's complement, 2's complement differences must be known, in which case it is positive, in which case it is negative. So in floating point number representation, the mantis of the number alone is truncated. So the truncation of floating point number is proportional to the number being quantized, in fact. So nt as usual, nt and unquantized, let me say nf is the floating point number, unquantized floating point binary number, and the truncated floating point binary number is actually ntf, something like that. Let us see like that. So the error will be represented in this case as follows. See, nf is the unquantized floating point binary number, ntf represent the truncated floating point binary number. So ntf is actually the unquantized number plus some relative error due to truncation of floating point number. So relative error due to floating point truncation will be given by this formula. ntf minus nf divided by nf. So the range of errors will be in this case. Range of errors will be in 2's complement positive mantis, you will get minus 2 into 2 power minus b to 0. Whereas in the 2's complement negative mantis, I will get 0 to 2. Whereas in 1's complement positive negative mantis, it is minus 2 into 2 power minus b to 0. Sign magnitude positive negative number mantis, I will find out that the value error lies within the range of minus 2 into 2 power minus b to 0. So these graphs, fixed point 2's complement number, floating point when mantis is 2's complement, fixed point number particularly 1's complement as well as in sign magnitude, and floating point number when mantis is 1's complement or in sign magnitude. These 4 different graphs will definitely give you an idea of how to put up the table with those values. The range of errors, it is called range of errors. So for all these values and the interval, the diagrams, you know that this is actually basically derived only from this particular. Any number that falls within this range is represented by this number alone. So the minimum is this and maximum is this, and the difference is actually the error, from which you can find out the range of errors. Anything for this range also, you can just take it out. This range is represented by this number, so obviously you can find out, right? So this graph is very, very, very important as far as the quantization effects by truncation is concerned. Thank you.